I'm a scientist in meteorology, atmospheric science, and climate. I have 25 years experience in this subject, and I can help you gain the skills quickly. That's today on High Peak Education. Let's do it. Okay, the topic is ocean circulation and climate. We sort of know that there's this big dialogue between atmospheric science and ocean science, between meteorology and oceanography. In other words, the ocean is the greatest storer of heat in the climate. It's often been said the ocean is the anchor of the climate. So what that means is long-term changes to the climate are always stored in the ocean in terms of heat and, to some extent, things like moisture, particularly heat, especially long-term heating of the climate. This is just a couple facts getting started. Low albedo, except when frozen. For water, it's not very reflective. Water is a key absorber for solar radiation. Absolutely. It's a reservoir of water. Yeah, absolutely. Of course, like the world's oceans are going to be the place where most of the moisture comes from for our weather systems. High heat capacity, lots of inertia. By the way, remember, water has the highest specific heat capacity among common substances. I have read that in some science books before. Now, I don't know exactly what is meant by common substances. Maybe to some extent it's like things that are naturally occurring worldwide. But in any case, water, as we know, takes a lot of energy to heat. But once you heat it, it stays warm for a long time. Remember, that's why we have daily lag and seasonal lag. If the water is warm, then if you live close to the ocean, the air temperature will stay warmer later into the day than otherwise inland, where you're far away from the ocean. And this certainly also happens on the seasonal time scale, right? This is why hurricane season is not greatest in July, even though that's the warmest temperature month in the northern hemisphere. Hurricane season for the Atlantic tends to be greater, as we know, in August, September, and then even a little into October, because we have that seasonal lag. And then ocean currents. Yeah, ocean currents is definitely important because the ocean is responsible for transporting a lot of heat energy poleward and bringing colder fluid, colder water towards the equator as well to even out the north-south temperature gradient. So that's a major role of the ocean. Ocean properties. Generally speaking, you would say that's a smaller temperature range in the atmosphere because, as we know, the atmosphere can get as cold as maybe negative 50 degrees Celsius and as high as maybe even closer to 40 degrees Celsius because water has a higher specific heat capacity. Usually, in most cases, the ocean isn't frozen. Now, it is more so towards the poles, but it's a lot more unfrozen than it is frozen. Okay, salinity is important. So this is different than the atmosphere. In terms of the ocean, because it has salt dissolved in it, that greatly affects the density of seawater. But then furthermore, the salt will mean buoyancy is not just dependent upon temperature. Buoyancy is also going to be dependent upon salt content. Okay, so the mass of dissolved salts in a kilogram of seawater is in parts per thousand. So that's the symbol, parts per thousand. Very similar to mixing ratios in the atmosphere. It's a small part of the mass is dissolved in a larger amount of the fluid. So 25 to 40 parts per thousand. I would have a rough idea of what those numbers are. A lot of times we will look at diagrams here soon and we want to know, just like the density of seawater. So density is a function of temperature, salinity, and pressure. Remember, water is a lot more nearly incompressible compared to air. As we know, one of the major differences between the atmosphere and the ocean is that gas is compressible, so we can greatly expand and contract air parcels, whereas water parcels, not nearly as much. As we know, distilled water, or 100% fresh water, we expect to have the density of 1,000 kilograms per meter cubed. As soon as we start dissolving salt into ocean water, the density is going to be closer to 1,025 or so. So it increased the density a little bit, and as it turns out, the temperature of a water parcel affects its density, whereas warmer water parcels are less dense than cold water parcels. And then the pressure, so think about this, right? the ocean is so heavy in terms of the weight of the ocean. When you're at a significant depth down into the ocean, you do have a substantial change in density because you have compression of the water parcels, even though, again, it's not nearly as much compression as the atmosphere. So one thing that's often done in the ocean is we do sometimes calculate things in convenient ways. And by the way, think of potential density in the same way we think of potential temperature or potential vorticity. It's kind of like could be released. Potential density is like, hey, if we get all the water parcels down to the same location, can we intercompare all their densities? Because that's the idea with potential temperature, right? Potential temperature takes out the pressure effects of the fact that air is located at different altitudes. So we want to compare air parcels one to the other to figure out their true temperature and thus their true buoyancy. Very similar with ocean parcels. In a similar way to potential temperature in the atmosphere, where we bring air parcels down to a reference pressure near the Earth's surface, with water parcels, the reference is the surface of the ocean. So in other words, to intercompare them, let's hypothetically bring them all up to the surface of the ocean to compare each of their densities. So again, we want to take away the pressure effects, right? Because we know that pressure is like a vertical coordinate, just like in the atmosphere. That as we go downward in the ocean, the pressure should be greater. I mean, if we go up in the atmosphere, the pressure should be less.